So in this example, let's work out what the reaction forces are at A, at A and B. Treating this as a UDL between here and here with a force of 2 kilonewtons per meter over a distance of 5 meters. So we can replace that with a central force there and a point force of 8 kilonewtons here. So that's a point force at the end of the UDL there of 8 kilonewtons. So if you can work out what those reaction forces are. Okay, so we have our reaction forces now at A and B. Hopefully you got those values. So now we can start drawing our shear force diagram. So we can put in the first reaction force at A going up to a 6.5. Nothing much happens until we get to the 8 kilonewton force, and then that comes down. And then we've got to take into account the UDL. Remember, that will start here and then finish at some value down here. So then we can draw in this gradient down there. And so see if you can draw the shear force diagram, and you'll know you're right because you'll end up back at 0 again. Hopefully you ended up with something that looks a bit like that. Going up to 6.5, which is that reaction force. Nothing happens till we get to here. Down 8, which takes us to minus 1.5. By the time we get to the end of the UDL here, we've gone down how much? 2 lots of 5 meters is 10, so we've got to go down another 10. So that takes us to 11.5. And how do we get there? Like that. Because it's a UDL. So the force is gradually being put on. And then the reaction force at B takes us back to 0 again. Let's think about our bending moment diagram now. It's going to start at 0 and end at 0. Okay? How am I going to find the bending moment? I find the area underneath the curve. What's the rate at which the bending moment changes? It's the value of the shear force at a point. So the gradient is given by the value of the shear force. So work out this area and tell me what the moment is by the time we get to this point here along the beam. .5, the area under the curve, under the shear diagram is 32.5. So by the time I get to this point on the beam, I'm at 32.5. How do I get there? What does the line look like on the bending moment diagram between those 2 points? Alex? Yes. What's the gradient of that line? Exactly, 6.5. If I go up at 6.5 for 5 meters, after 1 meter 6.5, after 2 meters 13, after 3 add another 6.5, 19.5, we're going to end up there. In other words, the gradient is constant, so it's a diagonal line with a constant gradient of 6.5. I'm emphasizing that because things are going to change here. If we look at this part of the curve, that's what's affecting us now. The gradient is not constant, it's changing. At that point, the gradient's minus 1.5. At that point, the gradient's minus 11.5. Minus 1.5 might look a bit like that. Minus 11.5 is going to look a bit like that, isn't it? So the gradient is not constant. What would it look like between these 2 points, do you think? A curve, yeah. A curve starting off flat with a low gradient and getting more and more negative until we get down to here. That's what it'll look like, okay? how do I know where I end up? Well, this is all going to be negative because it's below the line. So in theory, this area should add up to that because we're going to end up down at 0, aren't we? But to check that, we need to work out this area. Well, how do I do that? I've got effectively a rectangle and a triangle. So I need to split this into 2 bits, work out the area of each bit, and hopefully confirm that that comes to 32.5. Okay, so I'll just leave you while you do that and finish off this bending moment diagram. So hopefully you confirmed that we reach 0 by the time we get to here. Just a point on the mathematics of this function. The trouble with this is we freehand a curve in there. If I want to know what's the moment at that point, what's the moment at that point, what's the moment at that point, there's a big question mark about that because I've only put in a freehand curve. I know what the moment is here, and incidentally, we've confirmed that the value of the maximum moment coincides with where we cut the x-axis on the shear force diagram, as I mentioned earlier. So that gives us the point of maximum bending moment here. This is the value of the maximum bending moment, 32.5. If you remember what I said at the beginning of this gradient function here is what we're interested in. That will give us, if I integrate this gradient function effectively, I end up with a function that describes this curve. And if you think about this gradient function here, what's the equation of this line? Well, it's going to be something like y equals mx plus c, because it's in a straight line. We've looked at it already. M is going to be negative, and c is going to be the y-intercept, which will be somewhere up here somewhere. If I were to draw the line back, I'd find out where it cut that axis. So I could do it. I could find out what m is and what c is in this. And if I integrate this function, and if you remember doing the integration with me, those who did the maths with me last year, you'll know that by integrating x, I get an x squared, and that's a quadratic. And so if I plot a quadratic, I get this curve. And so that is a quadratic curve, a parabola. And once I've got that function, I could actually calculate exactly what the moment is at given points along that curve. But that's a bit further down the road. For now, and in most cases, really, when you draw these things in reality, you're really only interested in this value and maybe how it changes, but you're not really interested in the moment at particular points. In a beam, you're usually only interested in where am I going to get the maximum, because that's where I've got to make sure it's strong enough to cope with it. Okay.